Week 6 agenda. So for the lecture portion of the class, my plan is to finish a series loaded resonant converter today. Really hoping we can finish that today. So that Thursday we can also finish the parallel loaded resonant converter. I'll go faster on the parallel loaded resonant converter. So hopefully I can finish that on Thursday. The reason being, next week is your first midterm. I'll talk about that later. Weekly assignments. We have open lab this week. That's why I don't I haven't posted any lab manual yet on Canvas, because I'm thinking maybe for this week, since this is week number 6, it'll be good to do your final project, check-in. Maybe you can, or this week's lab sessions, you can work with your team to start your final project, right? And then ask questions during the lab sessions. Yeah, that way, hopefully everybody can progress in time, to be able to finish in time, I should say, for the final project. So please still attend the lab session this week and use the time to start your final project. Okay. Homework number 5, do this Friday. Quiz number 5, do this Friday as well. And as I said last week, the same thing here, do the practice quiz, right, to make sure that your web browser can display figures and equations properly. And then the quiz is going to be on chapter 3, specifically on series loaded resonant converter. Right, so just focus on series loaded resonant converter. So the question is going to be related to that one topology. So make sure you go over that before you go over this topic before you take the quiz on Friday. Midterm number 1, it's going to be next week, Thursday. Is that the right date? Sometimes I put the wrong date. It is the right date. 12:10 to 1:10. So 1 hour midterm, and then the remaining time will be used for you to upload, scan the test and upload, just like in EE411. You scan them and upload them to Canvas. It's going to be synchronous online test, open book, open notes, homework solutions, whatever you want to use for your test. You can use any other textbooks as well if you prefer. It's fine with me. Chapters 1 to 3, right? Calculations and conceptual types of problems. Don't know how many yet. It's going to be 3 to 4 problems. And as I said earlier, you'll download the test and then write your, just like in EE411, you write your answers on a separate piece of papers and then scan them and upload them to Canvas. Any questions on any of these? No? All right. Let's continue our discussion on series loaded resonant converter. I don't think I mentioned this last time. I actually helped design this topology one time for a company back in 1997. It was a medical equipment company. It was used for X-ray power supply, high voltage, from 3-phase AC to 120 kilovolts DC plus minus. So very high voltage, 40 kilowatts of output. And the topology that they use is exactly this topology right here, series loaded resonant. This, the isolated version of the topology. It's like this one right there. Okay, so that's what they used. That's what we use for that power supply. The power supply that goes into CT scanner in hospitals, right? That's what. Well, if you see one that's right now, the company. Well, back in maybe early 2000, the company got acquired by Philips Medical. So if you see any Philips Medical CT scanner, most likely, I don't know, maybe they have a new version, most likely, because that's been years. But the previous version, I designed I'll help design the power supply inside that CT scanner. Yeah, it was pretty interesting design, you know, high power, high voltage. And for high voltage, especially for high voltage, high power, this is the type of topology you want to use, right? For that kind of operating parameters, right? Input is 3-phase AC, and then output is high voltage DC, 40 kilowatts. This will be an ideal candidate to do the job right here. Okay, and especially for the high voltage, remember this is plus minus 120 kV, right? Okay. Imagine if you don't use soft switching, right? Then you'll get if you just use, for example, push pull or the standard bridge. Imagine the type of imagine the amount of switching losses you're going to get from this circuit if you are trying to produce 120 kV. It's going to be significant amount of switching losses due to the overlapping between voltage and current, right? Because voltage switches between 0 to 120 kV, right? Fast, and if that overlaps with the current, you can imagine the significant amount of switching loss that the topology will generate. So that's why for this kind of application, 120 kV, high voltage, high power, you typically don't want to use PWM topology anymore. That's too lossy, right? Switching loss-wise, it'll be too lossy, right? And we went over the simple model of this circuit, right? Oh, sorry, goes back. That in order to analyze this circuit, we're not going to use the original topology, but we simplify the topology by realizing that the input to the LC tank, right? The LC tank in series, that's series LC right there. Realizing that the input side flips back and forth between plus minus VD over 2, whereas the output flips back and forth between plus minus V out. Keep in mind that the input here is VD, and we have a half bridge. You can see this is a half bridge topology, right? We can also change or replace the capacitor with switches like that. So no capacitors, so it's going to be 4 switches, in which case you have a full bridge, right? If that is the case, then the input to this LC tank would be plus minus VD instead of VD over 2, right? So you just multiply any equations you see. If in any equation that you see in this chapter, if you see VD, you just multiply it by 2 if the topology is full bridge instead of half bridge. So I need to be clear on that, because those equations that we have in this book or in this chapter refers to half bridge topology, right? That's a half bridge topology, okay? So again, if it's full bridge, just replace VD with 2 times VD in any equation you see here. So same thing here. You see VD there. If it's full bridge, then replace it with 2 VD. So therefore 2 VD divided by 2 gives you VD, right? So for full bridge, it's going to be plus minus VD. Okay, and that's what we did last time. We simplified the model into a very simple model, right? Just like the previous soft switching, it has different states, but what's unique about these topologies that each state, with an exception of one state, there's actually 5 states. Each state, 4 out of 5, you'll see exactly the same circuit, which is an LC series resonant circuit with different input and output voltages, right? But the circuit is the same. The topology of the resonant circuit state is the same. It's just going to be like this, right? Again, the difference will be the input and the output, depending on, remember last time, depending on where the current is flowing, right? The direction of the current in the resonant tank will determine the polarity of the output, whereas the sign of the input voltage will be determined by which device is conducting at any given time. Yes, Nick.
I had a quick question
Yes.
backtracking a little on the application. You
Uh-huh.
said the CT scanner was powered by three-phase power.
Yes.
Why is that? Because I understand why three-phase power would be used for something like motors for like smoother power. So it's, rotating more continuously. But for something like a CT scanner, why would you use three-phase?
The main reason is this.
The power?
Yes. Imagine if you get 40 kilowatt from single phase. Can you imagine how much current it will be required by a single phase for this? A lot, right?
So more, okay.
So that's why you
Even
need
if,
three phase.
okay. If single phase was, say, a higher voltage that was equivalent to the three-phase equivalent voltage, would it be the same amount of current, or does three-phase offer an advantage past that?
Oh yeah, it offers other advantages, right? As we learned from EE410, because before it goes into this topology, it has to be rectified first, right? And we learned in EE410 that single phase rectifier is worse than three phase rectifiers in terms of many things, right? In terms of the quality of the DC out here, the output of rectifier, remember ripple frequencies and the ripple voltage, right? It's much better with three phase than single phase. So if you could get three phase rather than single phase with higher voltage, I would rather use the three phase with three voltages because you get much better quality. Going into this topology, you get clean DC.
Oh, you get cleaner DC coming out of three-phase too. It's not
That's
just an
correct. Yes.
efficiency thing. Okay.
Yeah. And keep in mind that this power supply is also being used for CT scanner, right? So you want this DC to DC converter to be clean from noise, especially especially audible noise, right? Because you're gonna put a patient inside the CT scanner, and definitely you don't want to annoy the patients with some audible noise from the power supply. So noise is a very important thing. In fact, they were having problem with noise, and then that's when they asked me if I had any idea on how to reduce noise. And that was the time I told them, let's do instead of bipolar, let's do unipolar. Remember bipolar versus unipolar by the end of E410, rather than switching from minus 120 kV straight to plus 120 kV. That's very high switching, but very large DVDT. Why don't we just use a unipolar switching, where you switch from minus 120 kV to 0, or from 0 to plus 120. So instead of straight, plus minus 120 like this, you go minus 20, 0, and then 0 plus 120, and go like this, right? So that would cut the noise level by a factor of 2. And so they were failing the tests, the standard tests with this type of switching. So I asked them, I proposed, to use this, and so they did. And I believe I told this story in E410 maybe, but unfortunately, I already left the company when they already tested this. But they told me that they were successful with this approach. If I was still in the company, I would ask for bonus, But they passed the test after they changed the switching to unipolar. Right. Does that answer your question, Nick?
Yeah. And you answered some questions that I didn't know I had. Thank you for giving me that intuition.
Oh, you're welcome.
It makes a lot of sense.
Yeah. All right. All right. So then we have the three modes: discontinuous conduction mode, depending on how big the switching frequency is compared to the resonant frequency. Then you can get three different modes. So not just states; these are modes different from the previous resonant circuit, right? Here we have three different modes. Discontinuous conduction mode, that happens when omega s is less than half of omega naught. And then continuous conduction mode 1, I'm just going to call it 1. I keep forgetting to put 1 here. So go ahead and put 1 and 2. That way you can differentiate between the two, because we have two different continuous conduction mode. So let's call it CCM1 and CCM2. CCM1 is when the switching frequency is between half the resonant and the full resonant. And then finally, a switching frequency larger than resonant. What is the difference between switching and resonant frequencies? Well, switching frequency is the one that we have control of, right? This is something that we can set. Omega naught, that would be determined by the selection of L and C, right? As you know already, resonant frequency is equal to 1 over square root of LC. So once you select L and C, then you have a fixed value of omega naught, right? So I don't think you could change this on the fly, right? This goes into the converter. So once you select those, then you cannot change those anymore, right? So you end up with a fixed resonant frequency. So based on how you want to place the switching frequency compared to resonant frequency, that would determine the operation of the circuit, whether it is DCM, CCM1, or CCM2, right? So let's look at let's look at DCM first. Let's just go straight to the waveforms, right? So here we have the, oh, I need to open another. So I need to go back and forth between, what did I do? Duplicate, there you go. So hang on a second here. I need to go to that chapter. I need to go back and forth between that waveform and the circuit. So I need to use two. I don't want to keep scrolling up and down. Where is it? Right there. Okay, there. Okay, so here's the waveform, right? This is the top waveform is the resonant capacitor voltage waveform, right? That's this voltage across that cap right there, right? And then the other one is current through that inductor, resonant inductor, right? So the bottom waveform is the current through the resonant inductor. And now you can see why this is called DCM, right? Why this is called discontinuous conduction mode. If you recall from EE411, how do you define discontinuous conduction mode? You define it by inductor current, right? If the inductor current goes to 0 and stays at 0 for some time, then it is discontinuous conduction mode. So you can see, here's the inductor current, right? You can see that at some point of time, inductor current goes to 0 and stays at 0, right? For some time before we turn the switch on again, right? So there's the discontinuity right there, right? Now, since every single state, before I go there, it's this waveform right here, it shows the timing, right? The time when it starts, so it reaches steady state. So I'm gonna start the analysis from t is equal to 0 right there, omega naught t naught, right? So that's the first critical point right there, right? And then the second critical point is omega naught t1, and then the third one is omega naught t2, and then t3, and so on and so forth, right? Now you can see from omega naught, when we start the analysis on omega naught t naught, t plus is being turned on. So this right here, this part of the waveform or graph shows which device is conducting at any given time. So from omega naught t naught to omega naught t1, you can see that t plus is conducting, right? Right there, t plus is conducting. Remember, we have control over this, okay? This is a controllable switch. So I could tell t plus to turn on at omega naught t naught. Then next is D plus is conducting. Now diode is not controllable, as you know already, right? So D plus will naturally conduct. And I'll explain later why D plus naturally conducts after T plus. And then after that, none of the devices conducting, right here, none is conducting. And then after some time, depending on how much output voltage you want, how much output power you need, that would determine when the next switch is going to be turned on, which is T minus right there, right? And then after T minus turned off, it's turned off, and then D minus takes over. And then none again, right? No one is conducting again. And then the cycle repeats, okay? Now, keep in mind that this switch, I believe I also mentioned that last time, that this switch is unidirectional. So only accommodates positive current for T plus and negative current for T minus, right? Remember we talked about it, right? I believe last time. So T plus will take over the, or can accommodate positive inductor current, whereas the negative inductor current is being accommodated by T minus, right? Okay, all right. What else here? Oh yeah, so then we have the number, 5 number of states of the circuit. Let me erase this, right? From here, I can see that I have a circuit that would correspond to this time segment. And then it changes to another state right there when D plus is conducting. It changes to another state when none is conducting. And then it changes to another state when T minus is conducting. And then lastly, when D minus is conducting. So you can see that 5 different states. 4 of them, remember I said earlier, four out of 5, right? This one, this one, this one, and this one, right? So all 4 except for the none. Those 4 states follow exactly the same LC, series, LC series circuit. Remember the model that we have earlier, right? Why do I need to draw? It's right here. So it follows this model with different input and output voltages, right? So those are the 4 different states. So every single state out of these 4 is resonant. It's always resonant. That's why you can see sine wave for each state. You see that? There's a sine wave here for state 1, sine wave there for state 2, and then the non is not resonant, so that's why it's just 0. None is conducting. And then another sine wave, that's another resonant, and then another resonant, right? Now, why are the peaks different? Well, because remember I said that the source and the output voltage, they change sign, right? Depending on where the current flows, as well as depending on which device is conducting. So imagine if you have the same LC series resonant, but the source is changing. Like if you change the source and you change the output, which contributes to the source, but if you sum them up, then of course that would correspond to different resonance, right? So you basically have the same, I can simplify this even further. You have the same LC, but any of those 4 states will give you different let's call it VX, like combined sources, right? So as long as L and C are the same, if you change VX, that's what we're doing, right? We're changing VX, which consists of VD over 2 and V out. If we change this, then of course the sine wave that is being produced by this circuit will also change. We'll have different peaks, right? Okay, so that's why you see that the sine waves have different peaks. Now, also note that the positive cycle, call it the positive cycle right here, right, is symmetrical to this cycle right there, the negative big cycle right there. And then the negative of the first resonant right there, cycle, first resonant cycle, is symmetrical to the second half of the second resonant cycle, right? So that's true because of the symmetry of the plus minus VD over 2 and plus minus V out. So the magnitude of the VX, the one that I tried to draw earlier, the magnitude of this right here, right? For this one, for that one, and for this one is the same, except one is plus, the other one is minus, right? Likewise, right, by symmetry, the magnitude right here corresponds to a new source, right? Corresponds to a new VX, right? And that new VX magnitude-wise is the same as this one right there. The sign is different. The first one is negative Vx. The second one is positive Vx, right? But the magnitude are equal, right? So that's why you have these symmetrical properties between the two peaks, right? The larger peaks, right? And the smaller peaks, okay? They're the same magnitudes, different signs, okay? And just like I did for the previous soft switching circuits, this is, these waveforms are not, I didn't draw these waveforms. I got these waveforms from ORCAD PSpice. I simulated the topology, and these are the waveforms that PSpice gave me, right? Okay. So I didn't make up these waveforms. This came out of the simulation. Any questions so far? And then we can go over what happens with the circuit, with the waveform when different devices conducting.
I had a question.
Yeah.
This is full wave, right? First of all.
Full wave. What do you mean?
This is like a full wave rectifier circuit rather than a half wave.
On the output side, yes.
Yeah. Okay.
On the output side,
Yeah,
but that's not shown.
Diodes.
Yeah, right here is full wave.
Okay.
Yeah.
And what is that Vx that's causing those smaller magnitudes? Like, what's causing that Vx to be different?
Well, different magnitudes, right? If you have different magnitudes of Vx, then you're going to get different equations for the sine waves, right? If you go let me duplicate this tab because I don't want to lose that page. It goes back to the beginning of the chapter when we talk about basic resonant circuit. What is it? Basic radio. Yeah, that one right there, right? That's exactly that, right? It's exactly this circuit. You agree?
Yeah.
Yeah. So if you change Vs, then you're going to change these peak values.
Yeah.
Right? So what is the equation? Right there. Right there. Right. So if you change Vs, then you can change the peak value of Vc, and you'll change the peak value of IL. See, IL is a function of Vs right there. Does that answer your question?
I guess I didn't ask my question properly. I'm wondering why there's like a big hump and then a little hump.
Yeah,
like why are those voltages differing?
Because the Vs is different, right? So one could be one could be VD/2 minus V out. The other one could be VD/2 plus V out.
Okay.
Right? If you combine the voltages, the input and output, right? So remember this?
Yeah.
Right. It's too crowded. Right. So depending on where the current flows, right, that would determine whether or not you got plus.
The two paths. Okay,
yes.
That makes sense.
That would determine if you get a plus or the minus, and then which device is conducting, that would determine whether or not you get the plus or minus on the input side. And then you would combine the two, right? You would combine the two voltage sources to give you the overall voltage source for the resonant tank, right? So that gives you the Vs here. That would give you the Vs there. So the combined effect gives you Vs there. Does that answer your question?
Yeah, that was the piece I was missing. Thank you.
Okay. So keep in mind that this Vs in this equation will be a combination of VD/2 plus minus, and also plus minus V out. That's what you put into this Vs. All right. Okay. Let's see what else. Okay. Any other questions? If not, let's take a look at the beginning of the waveform, right? When we turn on T plus, right? We're going to turn on T plus. So where's T plus? T plus is right there. Oh, let's not use that one. Use the non-isolated one. If you turn on T plus, that means you are allowing current to go positive, right? If you turn on this, that means you're allowing current to flow through the inductor and capacitor, right? To be a positive current, right? Aligned with this arrow. Right? So that's why the current resulting from T plus conducting, after you turn on T plus, will be positive inductor current. Okay, it's a sine wave because it's a resonance circuit, right? And then the same thing with a capacitor voltage. It also is a sine wave, right there. And keep in mind also that when T plus is conducting, right, that means current through T plus is the same as current through the inductor. Yes. So therefore, even though this is depicting inductor current, but at this point from here to here, that inductor current is also the same as T plus current. You agree with that statement? Let me know if you disagree. Right. So this inductor current is the same as T plus current, right? Because they're in series in this case, right? At this point. Okay. So just like a sine wave, it will go to positive, right? Sorry, it will gradually go up, reaches its peak value, and then it goes down, and it'll try to go negative, right? And it'll cross that 0 point right there. But when it tries to go negative, something happens, right? First of all, that negative current cannot be accommodated or facilitated by T plus, right? Because T plus can only allow positive current. You agree? So when current tries to go negative, T plus has to stop, right? T plus cannot conduct that negative current. So therefore, naturally, right, if current tries to go negative, right, crossing 0, right, tries to push negative, then I'm going to erase this. And even though T plus is on, it will be useless, right? Even though T plus is on, it will be useless because current cannot flow up through T plus, right? This is a unidirectional switch. But can we still have negative current? The answer is yes, because even though T plus cannot accommodate the negative current, but we have D plus that does, right? So instead of going to T plus, now D plus takes over, right? So naturally it does that without us forcing, D plus to conduct. D plus, as you know, is what's the word I'm looking? Non-controllable switch, right? So it will turn on by itself as soon as it sees negative current, and T plus cannot conduct negative current. D plus will take over the current, right? So that's why right here, starting from omega naught T1, right, for the negative current, you can see D plus is now conducting. See that D plus conducting. And then the circuit goes into resonant converter as well, right? The same resonant converter, this resonant converter right here, except now the source becomes different, right? Because now it flows through D plus. Therefore, you have plus VD over 2. Actually, it stays the same, plus VD over 2. But the output changes, right? When T plus is conducting, the output is plus V out because it's positive current. But now, since D plus is conducting, and we have negative current, therefore, as we already know, if we have a negative current, the output voltage changes to minus V out. The output voltage to this tank, right? B prime to B flips to minus V out. The source is still plus VD over 2. Because as long as T plus or D plus is conducting, AB will be plus VD over 2. But B prime B, when we have negative current, will be minus V out, right? So before it was plus V out. So right here, I'm going to put before and after. Before, when T plus is conducting, right there. I'm just going to use my pen. So this is when T plus is conducting. T plus is conducting, and this is when D plus is conducting. So when T plus is conducting, the input to the tank is plus VD over 2. The output of the tank B prime to B is plus V out. When D plus is conducting, the input to the tank is still plus VD over 2, but the output changes to minus V out, right? So that would change the peak of the resonance. So you can see the peak changes now to be smaller peak. Okay? So it's still resonating. It will still be sine wave, but the sine wave will have different peak values because the voltages are changing, right? Or the voltage, the combined voltage into the tank changes. Does that make sense, hopefully? All right. Okay, then what happens? Well, go ahead. Do you have a question?
Wait, so the output voltage that's changing is purely those 4 output rectifier diodes, basically which ones are conducting, right? Or
so
just to confirm.
Yeah. When I say output, it's actually output of the tank, not the output of the converter. The output of the converter is still
B prime, right?
Say it again.
You're talking about B and B prime?
That's correct.
Okay.
Yes. So when I say output, it's the output voltage of the tank, B prime B, right there.
Oh, I gotcha.
Yeah, right here.
That makes sense. Thank you.
Okay. All right. So then what happens next? Well, we have a resonant circuit again. So therefore, it follows sine wave, as you can see, with different peak, right? Smaller peak. And then sine wave naturally will go to 0, right there. And then it'll try to go positive now, right? At omega naught T2, following sine wave. Can it go positive? Well, we know at that time, T plus is no longer on, right? T plus is already off, right? So let's see. So now current tries to go positive again. Tries to go this way. Okay, right there. And so T plus is still off, and D plus, can D plus conduct positive current? Of course not, right? Because that would be blocked by that diode, right? That would be reverse of the orientation of the diode, right? So that positive current cannot flow through D plus anymore. That's why it has to stop, right? That's why D plus stops conducting. But what about T plus? Well, T plus is off, so therefore it cannot conduct, right? And that would be it, right? Or what about the other ones?
Is the circuit kind of halted until we turn on T minus?
Yes. So I'm trying to find different paths for positive current. If it cannot be provided by T plus, it should be able to be provided by D minus, right? Like that. You agree? So theoretically speaking, positive current can flow or can come from D minus, right? That way. But remember, this current has to flow back, right? And flow back, flow back, and they're gonna go up, right? And then there's no path anymore, right?
Wait, but since VC is like positive, oh, B prime would be the more negative cathode, right? Wait, would D minus be on or off in that case?
No, I'm just asking because I don't have, because again, current is positive, right? Current tries to go positive right there, right? Right here, current right there tries to go positive.
Right.
You agree? And then at that point, D plus has to be off because it cannot handle the positive current, and T plus is already off. So T plus is off, T plus is off, but yet the current tries to go positive. So my question is there any other path besides T plus and D plus? So I said theoretically, that positive current may come from D minus right there, yes? That far, do you agree? Well, that far.
And under the assumption that D minus was conducting, but we're not necessarily saying it is.
Exactly. I'm just saying that it is possible if D minus is conducting, then that positive current will be coming from D minus. But will it? Well, let's see. That current will go to the output, right? And it'll go back this way. See that? Coming back, right? That way into here. Oops. Oh, I messed up. No. Okay. Going that way, right? And then has to flow back either up or down, right? If it's coming back up to make the closed loop, it can't, right? Like actually, it can go downward, right? Right there, it can go downward and make the closed loop. Sorry, I'm confusing you. Let's do this. So theoretically speaking, right, that positive current can flow through D minus, going into the tank that way. It goes into the load, back to the tank, right? And then make the loop this way. There you go. That's what I'm trying to do. You agree? Yes or no?
That makes sense, yeah.
Yeah, but the question is, does D minus right now conduct, or is D minus right now conducting, or can, I should say, can D minus right now conduct current? Even though theoretically it could, but at this point, does D minus ready to conduct?
No.
How come?
Since the inductor current at that point is 0, I think, right? And VC must be at a maximum, which means that the anode of the D minus is higher than the cathode of D minus. Or I might have just messed up a bunch of negatives, but.
Oh, I see. It's interesting. The way you analyze this is very interesting. Okay. I don't know how to guarantee that voltage at this node is larger than this node, or is that true?
Because if the second
it is possible.
One was conducting.
You're right. That's true too. That's very good. So yes, because this is 0, right? That's 0 volts. And you get this positive voltage across VC. And if you have positive at that node, that means if this is 0 volts, that means you can see that the cathode voltage is also positive, right? And then the anode is negative right there. So therefore it's reverse bias. Very good. But the way I'm explaining it is different. But that works too. That works. The one that you explained is very good. Yeah, that's a different way of analyzing or proving that D minus is not ready to conduct. Another way to explain this is that as soon as IL goes to 0, let me erase this. As soon as IL goes to 0, then, and remember, T plus is already off. T minus is still off too, right? I'm not turning on T minus yet. If I look back to here, right, you can see that it's getting crowded. You can see that at omega naught T2, I'm not turning on T minus yet at this point, right? See that? T minus is not turned on yet. Therefore, if T plus is open, T minus is open, then what do you think the voltage is across T plus and T minus? Anybody? If there is no current in the circuit. So
VD over 2?
VD over 2, yes. So you got plus minus VD over 2 there, and you got plus minus VD over 2 there. Agree? If that is the case, look at what's sitting across T minus. It's D minus, right? So at this point, D minus is reverse bias, right? So you can also analyze it that way by using the input side. What you used earlier is this, which is again valid by looking at the waveform. I can tell that yes, at that point, voltage across cap is positive, and that would be the same as the cathode, and then the anode is negative. So therefore, it's reverse bias as well, looking at that point. Very good. But those are two ways of proving that even though theoretically speaking, the current may flow through D minus, but at this point, D minus is not ready to conduct yet, right? Because it's reverse bias. Any questions on that? No? All right. Oops. All right. So then that's why, because D minus is not ready and T minus is not being turned on, that's why once it reaches 0, right, the inductor current reaches 0, that means its charge is done, right? Therefore, it stays at 0 amp right there. And it's going to wait until we tell T minus to turn on. Right? So it will still be 0 until we want T minus to turn on. So in this case, in this example, I'm turning on T minus at T3, omega naught T3 right there. Right? Now we have a switch that is on, right? One of the switches. So if you go back to here, now we have this switch is turning on right there. Yes? If that switch turns on, then now we are connecting the source to the tank again, right? As soon as you have a connection between the source and the tank, now energy can flow through the tank. So energy will flow through T minus. Now you're forcing the two to resonate again. Resonant energy flows, and then it goes back that way, right? Making the loop. Okay? Any questions? So now you can see that at the start of, or right after T minus is being turned on, current has to flow negative, right? Because that's the only current that can be accommodated by T minus. And the same thing, you have resonant, right? As I said earlier, this peak right there is the negative of that peak. They're symmetrical. Right? And then the same thing, that current follows sine wave, and naturally it will go to 0, and it will try to go positive, but T minus cannot handle the positive current, right? So therefore, imagine if this current now tries to go positive, right? Right now it's going negative, right? It's going this way. But now it crosses 0, and it will try to go positive the other way around, right? It will try to go the opposite way. So now current flows positive. Can it? Well, yes, because this is still on, right? And then as soon as the sine wave tries to go positive, right, or crossing over, right, to positive, right away that current from going to switch, it will have to go through D minus to give you the positive current. Right? So that's why on the positive current, right, you have D minus conducting. Okay, and yeah, D minus is ready to conduct because its voltage is equal to 0, right? Because before that, T minus is conducting. Right? So that's why D minus can conduct. Any questions on this? And then the same thing, it's like before, you have resonant state, sine wave, it goes to 0 eventually, and then at this point we wait, right? Once D minus stops conducting, right? Because current tries to go negative, but at this point, D plus is not ready to conduct, right? Because its voltage is equal to VD over 2, and same thing with, it's actually equal to VD now that I think of it, because D minus is conducting. So then it will stay at 0 amp until we turn T minus, T plus again. So cycle repeats. Okay. Are there any questions? No? All right. So then the next thing would be to, let me think, what will be the next thing here? So hopefully now it's clear why why this D plus conducts after T plus and then none, right? And then why would all the devices turned off at omega naught T2? And then once everything turned off, then we can just wait, right? Until the next time we turn on T minus again. And now you understand why D minus conducts right after T minus naturally without us forcing D minus to conduct. And then the same cycle repeats. The next thing is, let's look at the type of switches. Now, if you look at this waveform, just focus on IL, right? This waveform right here, right? keep in mind that, as I said earlier, right, inductor current from here to here is the same as T plus current, right? And from here to here, inductor current is the same as T minus current. So my question is, first would be, could I use a semi-controllable switch, or should I use, or must I, am I required to use, or does this topology require us to use fully controllable switch, such as MOSFET? Right? So the question is, can we use thyristor? Remember, thyristor is semi-controllable switch. What is a semi-controllable switch? We tell the switch when to turn on, but then the switch will turn off by itself at zero current, just like a diode, right? So can we use semi-controllable switch such as thyristors for this? What is the answer?
Yes.
Yes, why?
Because we just need to tell it to turn on, it stays on until it becomes reverse bias. And then we don't have to worry about turning it off again.
Exactly. Very good, Cody. So yeah, you can see that current naturally goes to zero, right? We are turning off the switch at zero current right there. You see that? Once remember this hump right there is the same as switch current, right? So the switch current goes up and then it goes down. And then when it goes to zero, naturally current, right, moves to the diode, naturally turning off the switch. So even if you are using MOSFET, right, the diode will take over that negative current. So here is a good example where you can actually use semi-controllable switch. You're not forcing the switch to turn off, right? The switch turns off naturally like there at 0 amps. You see that?
Can you repeat what you said a second ago? Like even if you're using a MOSFET, D plus will turn on. Are you talking about a unidirectional MOSFET or?
Yeah, I mean, it is unidirectional, right? Even though you have the diode across it, but that diode is slower compared to this diode, D plus, right? So between the two diodes, D plus will conduct first.
Oh, I got you. We're always referring to unidirectional in this case.
Right, yes. So even if you have a MOSFET, let's say that the pulse of the MOSFET goes beyond T1 like that, right? That's beyond T1, right? And that MOSFET will turn off at T1 anyways, right? Because it tries to go negative, right? So either the internal diode of the MOSFET is conducting or the diode D plus is conducting. But of course you want to improve efficiency by not using the internal diode of the MOSFET, right? So you use a faster MOSFET across that switch. Is that good?
Professor?
Yeah.
Quick question. If the diode takes over right when the current and voltage becomes negative, why does the MOSFET not take over after D plus when the current and voltage would naturally go positive from that resonating circuit?
Right here?
Yeah.
Well, because I already tell MOSFET to turn off, right? So you don't want to do this. You don't want to have a pulse on the MOSFET to go all the way that way. Then yes, it will conduct, then current will go positive that way. Yes, I agree. So you don't want that. You want to control the MOSFET to turn off when diode D plus turns on. So something like this, like that.
Oh. But even if you have some error, that negative voltage will help. You just have to make sure it stays off after that diode stops conducting.
Yeah, exactly.
Okay.
Yeah. Yep. So as
Thank
long
you.
as you turn off the MOSFET right after D plus is conducting, then you're fine. Don't extend the gate pulse of the MOSFET to be above T2 like this. Right? That's not good. That's not going to make this circuit work properly. Okay. Any other questions?
Yeah, I had one question.
Yeah.
Could you clarify why the inductor current is smaller when D plus is on compared to T plus? Like, why is the second hump smaller than the first hump?
Well, we have a different combination of voltages, right? Earlier, I did this, right? When T plus is on, the source AB is equal to plus VD over 2, and the output of the tank is plus V out. So the combination of plus VD and plus V out gives you a larger peak than the time when diode D plus is conducting. When diode D plus is conducting, you have plus VD and minus V out. See that?
Yeah, that makes sense.
So yeah, if you look at the combined voltages between the two, then and then again going back to this equation right there, you can actually prove that mathematically over here too. Oh, actually right there, IL. Right, that's the VS right there. That would make it different peaks, and in this case less peak. Does that answer your question?
Yeah, perfect. Thank you.
Okay. All right. Then the next question is, can I use a PN diode for this one? Theoretically speaking, of course.
Which one?
PN diode. Do I have to use Schottky's?
Those aren't controllable, are they? Because you have to fire them, right?
Yeah, so for D plus and D minus, do I have to use Schottky's, fast diode, or would PN diode be sufficient for this mode?
You probably want pretty fast diodes so that you're minimizing that handover, right? Because otherwise the voltage is going to rise and then it's going to conduct and you're going to get a current spike.
Okay. Ideally though, theoretically speaking.
You also don't want a high turn-on voltage, right?
Yes, but everything's ideal here. So I'm saying theoretically speaking, meaning ideal. What can I use a PN here? Or is PN okay?
Theoretically, if turn-on voltage.
The inductor will just push the current through, right?
Yes.
So PN should be fine, right?
Well, the reason being, it is fine. PN junction should be fine here. The reason being, well, the diode, when it turns on fast. It doesn't matter if it's PN or Schottky or SBR, right? They're going to turn on fast. The problem with the diode is turn off. So focus on the turn off right there.
Junction capacitance?
Well, because of the reverse recovery time, right? Remember reverse recovery time of a diode, right? So if you look at the way the diode turns off, right? Look at what current does the diode turn off at? It turns off at?
0.
0 amps, exactly. So we're not forcing the diode to turn off, right? So if, let's say the diode is conducting current, let's say this is diode current, let's just say that's diode current. And then when the diode is conducting and we want it to stop immediately, this is the 0, then this steep change, that's when you need a fast diode, right? That's when
this is kind of dumb, but wait, a Schottky diode is just a faster diode, or is it like different voltage?
A Schottky diode is a fast diode. Reverse recovery is very short, like tens of nanoseconds, compared to PN that has around hundreds of nanoseconds. Right?
Oh, so like a factor of 10 faster.
Oh yeah, maybe more. So if the diode current reaches 0, when you turn it off, then what reverse current are we talking about? There is no reverse current, right? Because it goes to 0 naturally, right? So here, yes, on the first case, you are forcing the current to go from some amperage to 0 right away. In that case, yes, it will have, remember the reverse recovery time, right? But when the diode current goes to 0 naturally, and it turns off, right? And you don't want it to conduct anymore, then it will naturally go off, right? And in this case, there is practically no reverse recovery energy anymore because it's 0 amps, right? So therefore, for this mode, it is okay to use PN junction diode, a slow diode. Right? Because again, the current naturally goes to 0 when we turn off the diode. Does that make sense? right there. The
Yeah,
current
basically soft switching.
I don't know about soft switching, but basically we are not forcing the diode to turn off. That's what it is, right? Maybe that's what you meant by soft switching. So yeah, we are allowing the current to go to zero naturally, and then we turn off the diode, at that point. So there is no reverse energy right there, right? So that's why for this mode, it is okay to use slow diode. Right? You don't have to use Schottky's, which is an advantage. Remember earlier I said that this resonant converter is being used for high voltage, right? And Schottky voltage rating wise, I think Cody asked earlier about the voltage rating of the Schottky's. Schottky's diode voltage rating is not high, right? They're pretty relatively low, right? Around 250 volt max for Schottky's. PN, on the other hand, PN junction diode can go up very high, right? In terms of voltage rating, you can go up to tens of kilovolts, ratings. So for application that asks for 120 kV out, right? Plus minus 120 kV DC out, definitely you want to use PN junctions, not Schottky's. Because imagine if you use Schottky's, imagine how many Schottky's you would put in series, right? That's going to be expensive and not reliable, right? So for that kind of applications, right, it is useful to be able to use PN junction, because again, PN junction voltage rating is high. So here we have the benefit of operating the resonant converter in DCM, because we're able to use PN junction instead of Schottky's. Same thing
couldn't you just use a Schottky in series with the PN to get the high voltage rate? Oh wait, no, because it's as slow as the slowest.
Yeah, exactly. You're dragging down the Schottky's by putting it in series with PN, right? So the fast diode is useless because it's being dragged down by the slower diode when it turns on and off as well, right? And the same thing here, MOSFET and IGBTs, they don't go that high, right, in terms of voltage rating, also current rating, right? IGBTs probably can go up to 2,500 volts, but thyristors can go up to tens of kilovolts rating. So it is useful to be able to use thyristors for the switch and PN junction for the diode when it comes to high voltage, high power application. Right? And can you guess which mode we use when I work for that company using this resonant converter? Can you guess which mode?
DCM?
Exactly this mode. That's what we use. And there's more benefit, I'll show you later, with DCM. I think it's very cool mode to operate the converter with. There's also a trade-off, of course, but the benefits you get with DCM is actually a lot more than CCM. Okay, let's see, 5 more minutes. So those are the explanation I have. Yeah, try to go slowly because it's it's the first time you've seen this converter. All right, so the next, I only have like 6 minutes or so, right? Or 9 minutes. All right, so the next thing is, I would like you to understand how to determine soft switching property of series loaded resonant in DCM, right? Specifically looking at the turn on of the switch as well as turn off of the switch, right? When the switch turns on, does it have zero current switching property? If it's a yes, then I put a yes there. Does it have zero voltage switching property at turn on? If it's a yes, I put yes. If it's a no, I put a no. And for DCM, it seems like from this table, right? It looks like for DCM at turn on, there is no zero voltage switching, but there is zero current switching. For turn off, it looks like for DCM mode, GCS is yes at turn off, GVS is a yes at turn off as well. And of course, ideally or theoretically speaking, you just need one yes on each column, right? If you look at column turn on column right there, you just need one yes to give you zero switching loss, right? Because remember, switching loss is equal to V times I, right? Voltage and current when the switch is switching, right? So here, the voltage is a yes, but the current is a no. So here's a 0 volt, sorry, zero current, but the voltage is not, it's not zero. It's not zero, but that's fine because any number multiplied by zero gives you zero. Right? But of course, that's theoretically speaking, right? Real world though, it will be good if you have both yeses, both yes for both, right? So yes for both ZCS and GVS, such as the turn off right there. You can see that for turn off, when the switch turns off, it turns off at zero current and zero voltage. This is to guarantee that you have soft switching, that you have zero power during switching loss. Right? Even though, let's say that current is, yes, it's zero current, but imagine if the current is bouncing back, right? But if the voltage is zero all the way, then it doesn't matter if the current is bouncing back eventually to zero, you will still have zero switching loss, right? So just to ensure, to guarantee that you get zero switching loss, it'll be good to have yes for both ZCS and GVS turn on, as well as yes for ZCS and yes for ZVS for turn off. Okay? So what I'm going to explain in the next 7 minutes is how do I get to this? How do I fill out this table? Okay, so let's do. Well, before I do that, let's look at how zero current or zero switching is being defined. Let's say I have the current, right, with respect to time. This is time, right? And here's zero. This could be 0 amps, 0 volts, right? Amps or volts. Let's do amps first. So zero current switching is defined to be if, let's say, this is your this is the time t when we turn on. So let's do turn on first. When we turn on the switch, right there, at t equals to 0. What you look at is what happens before t0 and what happens immediately after. So what happens immediately before and what happens immediately after. If, let's say that immediately before t0, voltage, or sorry, in this case current, right? Current is up high, right here. And then when you turn, oh, sorry, current is, this is turn on. Let's do turn off. Turn off. Turn off is easier to explain. So let's say that before T0, before we turn off the switch is carrying a large current, right? Some current. And then at T is equal to 0, then we drop that current, right? Like immediately goes to 0 like that. And it goes to 0, right? So what we look at is what happens at T0 minus and T0 plus. If both are 0, then you have 0 current switching. If any one of those is not, then you don't have 0 current switching. Now go ahead and look at what happened at T0 minus. What is T0 minus? Well, T0 minus is the time when it approaches 0 from the left, right? So if you approach the time from the left into T0, right before T0 or T0, that's T0 minus. What is the current there? Is the current 0 or not? Right before T0, what is the current? Is it 0 or not 0?
Non-zero.
Non-zero. Exactly. It's not 0, right? But if you look at T0 plus, what is T0 plus? When you approach the time from the right into T0, right there.
0.
Right before T0, or right after, I should say, right after T0, that's T0 plus right there. What is the current there? Well, it's obviously 0 because it's turned off, right? So you can see that T0 minus is not 0, but T0 plus is 0. That's the case where we don't have no 0 current switching because one of them is not 0. As opposed to this, if let's say I change the current to sine wave, right? A sine wave, if you zoom in, right, a sine wave goes like this, right? But if you zoom in to that 0 crossing, right, then it's going to be like gradual change, right? If you zoom in, eventually it's going to go to 0, right? Well, something like this. I don't know if I can draw this like that. Eventually it's going to go to 0. Yes. So there's no steep change. You agree for a sine wave? Naturally, it's going to go to 0. So when you do T0 minus, what do you think is the value of that current?
Basically 0.
Basically 0 because it goes to 0, right? Sine wave goes to 0. So right before T naught, if it's a sine wave, if this is a sine wave, then that value of the current right before T0 is 0 amps. And then right after is also 0 amps, it's already turned off. So here is where we have yes for 0 current switching. Does that make sense? Anybody? Same thing with turn on, right? You do T0 plus, T0 minus. So if T0 plus, T0 minus are both zeros for turn on, then you have 0 current switching. You do the same thing for 0 voltage switching. What happens with the voltage at T0 minus and at T0 plus? If both are 0 voltage, 0 volts, then you have 0 voltage switching. Does that make sense? Okay, let's try just one and then we can adjourn. We'll go over this on Thursday. All right, let's see. Let's do turn on. It says yes there. So let's see if that's true. So turn on. Oh, let's see, I will have one right here. Turn on. So turn on is gonna be, oh, come on. You know what? I need to go to that waveform. I might be. Okay, turn on. Let's just do one quickly and then we adjourn. And we'll go over this on Thursday. Right there, where does, let's just pick one switch. Let's pick T plus, because they're symmetrical. So if you find out T plus, then T minus is gonna be the same. Right there, or maybe right here. Let's pick T minus. Let's pick T minus as the switch. So what happens when on T minus, when at T0 minus and at T0 plus? What is the current through T plus right before T3? What is the current?
0.
0, because none is conducting. See that? None of the device is conducting. So I know at T0 minus, before I turn on T3, I know that's 0 amps. What about T0 plus? What happens after you turn on T plus? Is it 0 amps or not?
It's sinusoidal, but because it gradually changes, so it's basically 0.
Exactly. This is omega naught T3, right? Current is gradually increasing from 0. It's not a steep change, right? It's going to increase, or in this case, decrease from 0. So if you do T0 plus, right before, right after you turn on, that's going to be 0, right? So therefore, because T0 minus is 0, T0 plus is 0, therefore, at turn on, we do have ZCS. It's a yes. That's what we have, right? And then we can adjourn. Is that what we have? At turn on, GCS is a yes. At turn on, GCS is a yes. Okay? Yeah, that will be it for today. So let's see if you understand that one first, this example first. If you don't understand it, you can ask it on Thursday, but that's basically how you determine ZCS and ZVS. That's just the first example. We'll go over the other 3 on Thursday. All right.